Well, you've learned some of the basics about thermal insulation now. You know what it does, and you know how it works. In the next few segments, we're going to be looking at how insulation relates to your job as a maintenance mechanic. We're going to discuss 4 of the most common kinds of thermal insulation and see how they're installed, removed, and repaired. The first kind of insulation we're going to talk about is calcium silicate. Calcium silicate is molded mass-type insulation. It combines lightweight with considerable strength. You'll see it used most often on high-temperature piping, like steam lines, because calcium silicate is high-temperature insulation. It can withstand temperatures of up to 1,000 degrees Fahrenheit or 540 degrees Celsius without burning or melting. Most plants have literally miles of this kind of insulation on its piping systems, so chances are you'll be working with it fairly often. Whenever you do, be sure to wear a filter mask and goggles to protect your lungs and eyes from dust, and gloves to keep the insulation from touching your skin. You see, many older installations of calcium silicate were made with asbestos fibers in the insulation. Asbestos is no longer used because it's been found to be hazardous to work with. So on older systems, you have to take extra precautions to avoid contact with the insulation. Since you're very likely to be working with calcium silicate, let's take a look at how it's installed. The insulation comes in half sections molded to fit around piping. The joints are staggered. Each joint on the right overlaps the 2 on the left. This makes the run stronger and prevents concentrated heat losses between joints. This insulation specialist is wearing all the necessary safety equipment. In case of slips, he's secured to the railing with a lifeline. The half sections are staggered, as shown before. Each section is wired to its opposite neighbor, locking the insulation together all the way down the length of the run. As the sections are mounted, they're loosely wired in place. Later, the wires will be twisted tight, and metal jackets will be banded over the insulation to strengthen the run and protect the insulation from damage. The next section is mounted on the opposite side. The end joints are butted together tightly so the insulation will prevent heat losses as effectively as possible. The first wire holds the section together, while the worker adds a second wire. Wires are spaced at intervals of 1 foot, about 1/3 of a meter. With sections of this size, that means 3 wires per section. To tighten the wires, he takes up the slack with his finger, then gently taps the wire all the way around to sink it flush with the surface of the insulation. When it's flush, he finishes tightening the wire with a few good twists, trims the ends, and sinks them into the insulation with a couple of taps. The remaining wires are tightened the same way. When all wires are tightened flush with the insulation, the mechanic measures the piece for a jacket. In this case, the jacket must fit around a steam pipe hanger. He cuts holes for the hanger and for the nut on the bottom. When the jacket is trimmed to fit, it's mounted over the insulation. Each jacket overlaps the other by 3 inches, about 7.5 centimeters. One edge tucks under the neighboring jacket, and the other edge wraps around the outside. This helps lock the jackets together while providing for expansion space between the joints. This is important because as the pipe heats up, the metal expands, causing the pipe to become longer. This tends to spread the joints apart, leaving gaps between the sections of insulation. The overlapping jackets cover the gaps and help prevent heat losses between joints. Initially, the jacket is secured with wire ties. Wires are twisted on about 1 foot apart, just to hold the jacket tightly in place while it's banded. Even though they're only temporary, the wires are put on the jacket the same way they were installed on the insulation itself. At first, the wires are loosely twisted on, just to get their approximate position. Placement of the wires is not critical, but you have to think ahead. The bands go on next, so the mechanic makes sure to leave room for them by visualizing where they will go in advance. The bands will go between the wires, and then the wires will be snipped off. In this example, bands will be placed on either side of the pipe hanger to hold down the flaps, so wires are placed slightly further down the pipe, holding the flap tightly enough while still leaving room for the bands. When all the wires for a single jacket are in place, they're twisted tightly so the jacket fits snugly, but not so tight that the wire breaks. Remember, the metal jackets don't give like the insulation itself. The wires aren't embedded in the surface. The object is to hold the jacket in place so it forms a smooth, tight shell over the insulation with no buckling or loose spots. When the jacket is firmly in place, it can be banded. Bands are placed 1 foot apart, about 1/3 of a meter. Additional bands may be needed to hold down flaps from special cuts, like the cut for this hanger and the ends of the jacket. The first step is to position the bands. When they're all in place, they'll be tightened with a special tool. The mechanic wraps the band around the jacket and pushes the free end through the slot. He pulls on the free end to cinch the band tight and bends it up so it won't slip back through. At this point, it's not vital to get the bands extremely tight. The banding tool does that. What you want to do here is position the bands correctly and secure them loosely over the whole jacket. Just slip the band around the jacket, pull it tight, and bend the end up to hold it in place. Don't bend the soft metal back and forth unnecessarily. Metal fatigue will cause it to snap. This is a banding tool. Spreading the handles one way pulls the band tight. Pulling them in the opposite direction cuts off the free end of the band. The stub is bent over to keep it from pulling through, and it's held down by 2 tabs on the slot. Remove the piece of scrap from the banding tool and you're ready for another one. Slip the end of the band between the jaws and through the slot on the rotating piece. Spread the handles slightly as you bend the end down in line with the direction of pull. Spread the handles, bend the end up, and pull the handles the other way. Bend the end over so it won't pull through, and secure it by tapping the tabs down over it. This is only one kind of banding tool. Several different kinds are used, but they all do the same job. Pull the band tight and cut off the end. Whatever kind you use, be careful not to stretch the band so tight that it breaks. With practice, you'll learn just how tight the band can be without snapping. When all the bands on the jacket have been tightened, the mechanic removes the temporary wires. The bands should hold the jacket on so it's smooth and tight, no bulges or buckling. Jackets are mounted differently on vertical runs. To keep the jackets from sliding down the pipe, 3 S-clips are hung on the jacket below. The clips are made from scrap pieces of band, bent sharply at either end. The jackets overlap just as before. The clips support the weight of the jacket. At first, the jacket is secured with wires. Wrap the wires loosely. Then, tighten them so the jacket fits snugly over the insulation. The bands are positioned loosely. Tightened with the banding tool, and the wires are snipped off. Most calcium silicate installations are jacketed with metal, like the job you've just seen, but this isn't always the case. Sometimes the insulation is covered with canvas cloth called lagging. Sometimes straight runs are lagged, but more often lagging is used on elbows and other fittings where it's difficult to mount a metal jacket. Since these are the areas where maintenance is most frequent, you'll need to learn the skills for insulating these places. What we're about to see is a routine maintenance job on a lagged section of calcium silicate pipe insulation. The workers will be using 3 special materials: lagging cloth, insulating cement, also called mud, and finishing cement. Notice that the corners of this section are white. They're covered with lagging. A metal jacket covers the straight section in between. The first step is to remove the jacket. This jacket has been fastened with self-tapping screws instead of bands. They're taken out with a screw gun, and the jacket is removed. Next, the lagging is slit and peeled off the insulation. Then the wires are snipped off. The straight section of insulation is sawed off, since only part of it needs to be replaced. Then the outer layer can be removed. All scraps of used insulation are set aside to be properly disposed of. This insulation was installed in 2 layers to reduce heat losses to a minimum. The inside layer is removed the same way as the outside layer. The wires are snipped off one by one, and both halves are taken off and placed in plastic bags for disposal. The elbow was covered with insulating cement called mud when it was originally installed. The old cement must be chipped away before the wires can be removed. Each wire should be peeled off of the insulation to break up the mud and make the sections easier to remove. When the last wire is cut, the insulation can be taken off with no trouble. The pipe is inspected for cracks and corrosion before it's covered again. Before the insulation can be replaced, the new elbow insulation must be carefully trimmed to fit around the riser and the weld bead. Then, both halves are fitted over the elbow. If they've been trimmed correctly, the insulation fits close to the pipe all the way around, and both halves mate together with no gaps. The halves are wired together loosely. Then the wires are tightened and sunk flush with the surface. The straight gap is measured so new pieces of insulation can be cut to fit. The new sections are cut with a standard rip saw. The insulation is mounted on the pipe, and the wires are tightened, just as before, flush with the surface of the insulation. The outer layer is put on so the seams do not match up with those of the inner layer. This helps prevent concentrated heat losses through the cracks between halves. The insulation is then wired on in the normal manner. Insulating cement is used to fill the remaining cracks. The mud is usually mixed up by hand on the spot in the exact quantities needed for the job. It's troweled into the cracks to seal off possible heat leaks and smoothed over the entire elbow. With a steady hand and a good eye, it's possible to form a hard, airtight shell that makes a nicely rounded, smooth surface for lagging. Before the elbow can be lagged, the lagging cloth must be cut to the correct size and shape. The worker measures the lagging cloth by laying it out against the elbow. Then the cloth is folded into a triangle and doubled over 3 times. The lagging is cut to the correct length with a sharp knife. When the cloth is unfolded, it forms a quarter circle, just the right shape to stretch over half of the elbow. The lagging is thoroughly wetted with finishing cement. It's brushed on almost like wallpaper paste. This mechanic uses a thin coating of cement on the box to hold the cloth in place while he wets it down. Next, the cloth is fitted to the pipe. It's smoothed down so no wrinkles mar the finish, and carefully trimmed to fit around irregularities. Finishing cement is then brushed over the outside of the lagging to stiffen the cloth and give the elbow a neat appearance. After lagging the other side of the elbow, all that remains is to replace the metal jacket on the straight section. The length of the section and the insulation circumference are measured with a tape. The jacket is cut with snips. Secured to the insulation with self-tapping screws, and the job is complete. Well, we've spent a lot of time on calcium silicate insulation. That's because it's probably the most commonly used type of insulation in your plant. When you're working with calcium silicate, you'll need all the skills you've seen demonstrated here: installing sections and jackets on horizontal and vertical runs, and the lagging techniques that are usually used on corners and awkward fittings.